In third semester calculus, we learned a different way on how to do optimization problems. It's a little bit more efficient. No, we need partial derivatives. You guys can.
We also do this like in just like 130. I remember a problem like this in 130.
Except that this is going to be using calculus to do it. But there's other ways to find some optimization. So I want you to visualize. There's a lot of different rectangles that we could draw here. Like a thin one, a really small one that's really tall, and still have the same amount of fencing. Each one's going to change the volume of it, or not volume, the area that is surrounding. So I'm going to call this X and this Y. There are two things going on here. We have area that's enclosed, and we have perimeter, right? Length around it. For sure, the perimeter has to be what? 2400. Firm wants to use it. Use it all. And there's lots of combinations that we could do to get 2400. Okay? So the perimeter is going to be 2x plus y. That's going to be constant. What's that equal to? 2400. Yes?
Would it be the same thing no matter how you draw it, how you said? You said you can draw it like 3 different ways.
Yes, and you could draw an infinite number of different ways and still get 2400. That's why I left it x and y. It's always going to be rectangular, so this side will always be the same as that side. It's just it may shrink and get wide, or it may go tall and thinner like that. Yes?
I'm having a hard time realizing that I understand there's two sides of x, and so that gets factored in. But why do you only have one side of y when you're
because
not?
The river's on the other side.
Oh, it's a river.
We're not trying to block out the river.
Okay. No river. Gotcha.
Yeah.
Hello, blue.
Yeah, this is the extent of my artistry. So we have 2x plus y equals 2400. Now, what we're going to do next is I'm going to talk about area. There's two pieces, right? Perimeter and area. The area is going to be what? X times y. And we talk about local mins, local maxes, minimums, maximums, things like that, just like the problem that we just did. This is a local maximum here. We want to maximize the area, right? It's the same thing. We're going to want to take a derivative and set it equal to 0 and figure out what we get. That's going to be where our maximum or our minimum is going to be. Now, I want to take the derivative of a in this case, because that's what I'm trying to optimize, the area. I want the biggest area. But we don't know how to take the derivative of a function with two variables. It can be done. Third semester calculus, we do it a lot. But right now, area is dependent on two variables, x and y. We can't have that. So we're going to have to solve this problem somehow. Since this is constant, I am now able to rewrite one in terms of the other. To give me this. We kind of did the same thing with the R and the H. You remember that with the cone? Where we set up the symbol of triangles, we rewrote one in terms of the other, because the information that we were given. Now area is solely dependent on x, which are the two sides. Now I can take the derivative to try to optimize it. So I'm going to take the derivative of a with respect to x. optimize it, I want to go to where the slope of the tangent line is 0. I want to optimize it. So I'm going to set this equal to 0.
Sorry, I wasn't listening. Why do you set it to 0?
Again, same reason we set the derivative equal to 0 here, we're going to get a local minimum or a local maximum. Now we can verify that it's a maximum that we're getting. We got to set up for it increasing, decreasing, and all of that. But for right now, we'll bypass that and just hope. It's a very math scientific thing.
Incredibly precise.
So one side is 600, the other side is 600. How do we figure out what this is going to be?
Plug it in.
You're going to plug it in. I have no idea what that's going to be.
Into the derivative, right?
So here are the dimensions to give us the largest possible area. I'm going to start from the beginning and walk through it. Yes?
Joel made a comment. He said you plug that into the derivative, but you don't. You plug it into the original y value, correct?
That's what I did.
Okay, because I'm just confused.
Yeah.
Yes, sir.
X equaling 600 feet in reference to the constant, does that create a ratio that is an identity for optimization?
That's just a lot of math work. Say that again.
The ratio that 600 is to the 2400, where those variables are used in referring to a rectangle, is that ratio definitive of all rectangles?
I'm not following you, man.
Is there a rule that can be derived from this calculation that will explain how to optimize a three-sided rectangle?
Perhaps. I do not know of one. Probably. If I'm understanding your question.
Yeah.
Okay. Let me walk through this one again. Let's start out with the actual problem. What the problem is saying is that this farmer has only 2,400 feet of fencing. Okay, that's a length, right? And he wants to fence off a part of a river, so he only needs 3 sides. That's a rectangular in shape. But he wants to optimize the area. Okay? Maybe he wants to keep his, so his livestock can drink and eat, and, the area and corral it, whatever. Okay? So to find the largest area, there are many areas that are going to be less than this. In fact, if we pick any other dimensions for this that gives us a perimeter of 2,400, it will be less. Yes, someone's hand went up. And by the way, if we want to know what that area is, we just multiply these two. And we have so many square feet. But the problem wanted the dimensions. So what we did was we figured out, we understood the problem enough to draw a picture. The perimeter is going to be x plus y plus x, which translates to us 2x plus y, which is equal to the constant. I rewrote this so that one variable was in terms of the other. This is going to be same type pattern for all these various problems. Next up, I go to what I want to optimize. I remember when I was doing this, I was always like, which one am I taking the derivative of, the perimeter or the area? It's always going to be whatever it is you're trying to optimize, largest area. So area is what I'm trying to optimize. The area of this rectangle is x times y, making the area dependent on 2 variables, which at this stage we're not able to handle. So by rewriting one in terms of the other and dumping it in, I've changed the area is now just a function of x instead of x and y. To optimize the area, I have to take the derivative with respect to x. Just like if I want to find the slope of the tangent line, that's equal to 0, I have to do the derivative first. Then I set it equal to 0 because, again, that's going to get us our local mids, local maxes. Anyone through? Solve the problem. I'm going to try to get one more in before